So in today's lesson, we are going to attempt to learn carboxylic acid and esters. We have, in a couple of chapters ago, when we studied alcohols, considered carboxylic acids. We said that alcohols could be primary, secondary, tertiary, and we actually did reactions of these, and primary alcohols would oxidize to yield what? Aldehydes. Very good. And aldehydes, furthermore, would oxidize to yield carboxylic acids. So again, we are going to revisit carboxylic acids. This is a new module that will study them, and it will also study esters, and that one's new. Okay, so carboxylic acids will be a review, and esters will be new. In order for us to remember what an acid was, I am going to bring you back through memory lane and differentiate an organic acid from an inorganic acid. Carboxylic acids are organic acids, as opposed to an inorganic acid. What do you think the difference between these are? Exactly, the presence of carbons. Exactly right. So an inorganic acid would be something like HCl. If I have HCl, remember hydrogen chloride had a covalent bond. Hydrogen has how many valence electrons? 1. And chlorine has 7. 1, 2, 3, 4, 5, 6, 7. And we said that if we put it in water, that covalent bond breaks and a hydrogen ion is donated. So we had an inorganic acid that yield hydrogen ions and chloride ions. So that extra electron, we probably put that as an X, that belonged to the hydrogen before. It's now part of the chloride ion. So an acid was defined as a substance that releases hydrogen ion. Okay, and that is still true. But now we're going to be looking at organic acids, not inorganic acids. So it's the very first organic acid that we are going to consider is ethanoic acid. Who can write the structure? Go ahead and write ethanoic acid. We'll all write it together. How many carbons? 2 carbons, and the carboxylic acid has a C double bond O, single bond OH. This right here is a carboxylic acid. And a carboxylic acid is an organic acid but just like any acid, a hydrogen ion will be released, and this is your acidic hydrogen. But now I have a double arrow as opposed to a single arrow. When I had a single arrow, I had a strong acid, meaning I had 100% ionization. Remember that? But when I had a weak acid, I had an equilibrium. I had an arrow going forward, an arrow going back, meaning if I have 100 of these molecules, maybe 2 or 3 or 4 will break up into ions. The other 97 are still covalently bonded. So I am going to be left with ions after the hydrogen ion is released. So an acid, whether it's organic acid or inorganic acid, is a substance that increases the hydrogen ion concentration, releases hydrogen ions. So I have hydrogen ions in the product side after the arrow. Organic acids are weak acids. This right here is present in vinegar. Ethanoic acid is present in vinegar. Vinegar is a mixture that's like a 5% solution of ethanoic acid. Ethanoic acid is also called ethanoic acid. It's also called acetic acid. So this is an organic acid, and if you put this in water, the pH will be below 7, like any other acidic solution. Still going down memory lane. Remember, acids reacted with bases, and we call that what? A neutralization. Very good. So I'm going to go back to HCl, and I'm going to react HCl back in memory lane. HCl is going to react with NaOH. Tell me if I have HCl plus NaOH back module 6, I believe. This was a double replacement. You switch your partners. This was a neutralization reaction. What were the products of the neutralization reaction? Who remembers? NaCl and water, and HOH. Okay, so an acid reacts with a base to give you a salt and water. That is not new either. The only thing we're going to change is we're not going to have an inorganic acid, we're going to have an organic acid. So let's do the exact same thing now with ethanoic acid. And when I said ethanoic acid, I could have had propanoic acid. How many carbons in propanoic acid? 3. Or butanoic acid. How many carbons in butanoic acid? 4. Or pentanoic acid. 5 carbons. But I still have my carboxylic acid group. Okay, so let's go ahead and rewrite ethanoic acid and react it with sodium hydroxide. So I'm going to go back to do a neutralization reaction, but now with an organic acid. So I'm going to have CH3, C double bond O, single bond OH. So remember to show your bonds. This is your carboxylic acid group. And when you react it with sodium hydroxide, I'm still going to produce water. So these two will yield water. And what else do I have? I have left this CH3, C double bond O, single bond O minus with an Na plus, and my water. I can write water as HOH or as H2O, is the same thing. These two things are identical. We know that. Okay, so this is an organic salt, and this is an organic acid. But anything that an acid did, release a hydrogen ion, neutralize with a base, it's still in place. Organic acid, like ethanoic acid. And this is a salt called sodium ethanoate. Thank you so much. Did everybody sign the class roll? Okay, so let's go back. Please sign the class roll. Okay, so up to here we're okay? No problems? Okay, we're still going down memory lane.
Is it critical to put the positive and negative?
Yes, it's good to put the positive and the negative in your salt. Okay? I am going to remind you, how did we form a carboxylic acid? We had said things in the past. Formation of carboxylic acids. And we really started with an alcohol, oxidizing it to a what? An aldehyde. So we started really with a primary alcohol. This is how we approached that oxidation reaction of alcohols. We put brackets O in the arrow, meaning we have potassium permanganate, potassium dichromate. We have some kind of oxidizing agent, and the primary alcohol produced an aldehyde, and the aldehyde continued to oxidize and gave us what? A carboxylic acid. So that's why this module didn't sound like a new module, because we've had this before. We've had acids before, we've had neutralization reactions before, we've had formation of carboxylic acids before. But in here, we're really going to make a stop and look at the properties of carboxylic acids. See what they have to say to us. So let's go ahead and form ethanoic acid from a primary alcohol. So let's go back to forming ethanoic acid. So what alcohol would I form? CH3, what? C, a primary alcohol. So I have a single bond OH on an H, on an H. Let's pretend those H's come out as H's. A primary alcohol is remember you have an OH in a carbon that's bonded to either no carbons or only one carbon. And when we oxidize that, we produced an aldehyde. And what was that? CH3. So this is a good review for our test coming up next week. That was an aldehyde. That's an aldehyde. That's the primary alcohol. But now, this is where we really need. This is module 12. How do we form a carboxylic acid? By oxidizing an aldehyde. You can oxidize an alcohol fully and go all the way to a carboxylic acid, or you can start with an aldehyde and you still end up with a carboxylic acid. So, whoops. I don't know, where was I? This one? No. This one? Yes. Okay. So let's write the oxidation product. CH3. C, and then the double bond O stays, and the single bond H changes to an OH. So that's my carboxylic acid. So that is not new. Now let's go to the book. Example maybe 3C. On module 12, we are in module 12. No. Okay, in 3C, I have formation of a carboxylic acid. So we're reviewing what we just saw. How do we form a carboxylic acid? And the reagent that's starting us in example 3C has a parent chain of 4 carbons. I have a couple of methyls in carbon 2 and 3. I have an aldehyde group, so I'm going to put a C double bond O single bond H here. So noticing that in this reaction, like in all the other reactions, I'm showing all the bonds to see what is changing. The first one has just 3 hydrogens. And when I oxidize it, what do I produce? So if you have this in your test, what is your product? CH3. Oops, good. I'm missing an H there and another H there. CH, and that has a methyl. And the other CH, that has another methyl. And then a C double bond O, what else? Single bond OH, perfect, you got it. So I have an aldehyde oxidizing to a carboxylic acid. And that's not new, right? We did this in the past. Any questions there? Okay, so then let's go do something new. Let's move on. We said at the beginning that we had acids, carboxylic acids, and esters. Okay, so I want to see if we can go. We're all the way there. I'm here now. Esters. We're going to look at what esters are. let me go ahead and, I don't know if this is going to work. Let me try this. Make it big. Nope, that didn't work. Get it out.
Dr. Johann,
Yeah.
that, the extra oxygen to form the carboxylic acid, does that come from whatever the oxidizing agent is?
Right. Yeah, that extra oxygen comes from my potassium permanganate, comes from my potassium dichromate. I will have some kind of oxidizing agent. And I should have done more than one template here. Okay, so this is like okay. Erase, erase, erase. And formation of an ester. Are you following me in the book? What page am I in? 219. Everybody is in page 219. Oh. Okay, check that page 219 and tell me. 218? What are the reagents necessary to form an ester? A carboxylic acid and an alcohol. Okay. So we're already done remembering what carboxylic acids are, and now we are going to form an alcohol. Form an ester. We're going to form an ester reacting a carboxylic acid and an alcohol. Okay. Carboxylic acid plus an alcohol, and the alcohol is going to be maybe white. It's going to produce an ester and water. Let's see what we mean by this. Let's go ahead and write a carboxylic acid like ethanoic acid. So let's rewrite ethanoic acid, CH3, and then what? C double bond O, single bond OH. And let's combine that with methanol. Methanol has how many carbons? 1 carbon. And how many OH groups? Only 1. So this is my alcohol, and this is my carboxylic acid. If the OH of the carboxylic acid and the H of the alcohol form water, so this is a dehydration reaction. We really need a little acid for this reaction to go on, a little catalyst. So on the arrow we want H plus, and this is a dehydration reaction. So I am going to put on the arrow my conditions, which is an acidic medium, and I am going to remove water. I'm going to put minus HOH. The H of the alcohol and the OH of the carboxylic acid combined. So what am I left with? CH3, C double bond O, single bond, and now I go to my oxygen, which belonged to the alcohol, and my CH3 that belonged to my alcohol. This right here is my ester. And I knew I wasn't going to have enough room, so I put minus water and the arrow If you have room, you can write plus water as a product. Okay, so either write plus water or minus water. So this is a dehydration reaction. What did that mean? We're removing water. We're removing an OH from the carboxylic acid and an H from an alcohol. Okay, so as long as we show the bonds, this is easily followed. Correct? Are we okay? Okay, let's drill this. Let's go back to the book and do example maybe 5B. In 5B, okay, esters are a totally different functional group than what we have seen so far. So we've seen alcohols, and alcohols is a family of their own. Okay, we've seen aldehydes, that's a family of their own. We've seen ketones, we've seen carboxylic acid, so I don't care if I have a carboxylic acid of 2 carbons, ethanoic, or of 3 carbons, propanoic, those are all a family. Esters is a whole different functional group. Esters have very pleasant odors. Like if you put perfume this morning, that's an ester. If you smell a banana or a fruit, pineapple, those are all esters, okay? Lotions have ester groups, they're very pleasant odors. And they have a C double bond O, single bond OCH3. I'm going to rewrite this in a condensed version without putting the yellow and the white, because in a test you don't have 2 colors and you are supposed to recognize them. Okay, so it may look a little bit different. If I condense the carboxylic acid, remember it looked like that. It kind of looks a little different. So COOH is all one big thing. And the alcohol, methanol, many times you put it like this. But you're still going to get the H on the OH. And you're still going to bond those 2 together. So you're going to get the CH3, COOCH3. So that's condensed as opposed to showing the bonds. So like always, rewrite your notes, showing the bonds, following what happens, but then go ahead and condense them, because your test is going to have esters like this. This is an ester. This is identical to that. This is identical to that. And this is identical to that. Okay? In your test next week, you will not have to name esters, but somebody asked me how to name it. To name this ester, you name this branch here, which is a methyl, and this is an ethanoate. So it will be methyl ethanoate. But don't worry about that. That's not in your test. Okay? I told you up to, I think, carboxylic acids. Okay, so we were doing example 5B. Do we do it in white or do we do it in 2 colors?
No, white.
In white, because that's really where you need to go to. Okay. So we're going to go to example 5B from the book. And they are showing your bonds, so they're being very nice. CH3. We have 3 carbons. Carbon 2 has a methyl. Okay, and they are showing your carboxylic acid group. And the alcohol, I'm missing an H, thank you. And then the alcohol is cyclohexanol. So go ahead and write cyclohexanol. You have a cyclic compound. And I go ahead and put them side by side, so I can circle the H of one and the OH of the other one and dehydrate. Okay, so on the arrow, I must write my conditions. Since my water doesn't fit in the screen, I'll just write it minus water on the arrow. And the H's. Minus water. So what do I have? I have a CH3, a CH with a CH3 up here, and a C double bond O, and a oxygen attached to my cyclohexane. So it looks kind of funky. But that's what's resulting. Not so bad? Formation of an ester? Okay. The only really new thing that this module has is formation of an ester, and then we're going to go back. We're going to dehydrate. So if we call we're doing a hydrolyze. If we call it formation of an ester, the reaction between a carboxylic acid and an alcohol, if I go back, if I'm going to go this way, I'm going to hydrolyze an ester, what am I going to form? An alcohol on a carboxylic acid. Okay, so my next section is going to be hydrolysis of esters. That's the exact opposite of the formation. Okay, so hydrolysis of esters. Okay, so this is exactly the reverse of the formation. Okay, there are two types of hydrolysis. The first type is going to be on acidic medium, acid hydrolysis. And the second time would be what? Base hydrolysis. Okay, so like always, the term hydrolysis, lysis, from the Greek means breaking. And you're breaking what? A bond. With what? With water. Okay, so instead of dehydrating a carboxylic acid and an alcohol, you're adding your water back into your compound. And in this section right here, the H of the water will go back in there. And in this section right here, the OH will go back there. So you'll go back to your carboxylic acid and your alcohol. Okay, so let's go ahead and write it. And let's write it under acidic conditions. Okay, so acid hydrolysis goes first. And I'm going to have my CH3, C double bond O, single bond, and then I go with my white guy. O, oops. Or do it in one color. One color? Gutsy guys, good. Okay, so that's my ester, yes? And I am going to add water. Plus water. HOH. And where is the H going to go? To the O. And where is that OH going to go? To the carbonyl group. So go ahead and write that as your products. If you dehydrate, you also need to add a little acid. So your two products are your carboxylic acid, your CH3, C double bond O, and now that bond is gonna break. You're breaking that ester bond. And the H of water goes and forms your alcohol. So you can flip them. I'm going to go ahead and flip it. Instead of writing OHCH3, I'm going to write CH3OH. In the answers of the book, I do that a lot. I flip the alcohols and I put them upside down. So you're thinking in 3Ds as opposed to linearly. Are we following this? It looks a little different when it's in one color and when I flip things around, but again, and this could be condensed as CH3COOH all in one line. Any problems in there? We did nothing new, really, just the reverse of the formation. Not so bad? Okay. Now, base hydrolysis is a little bit different. In base hydrolysis, I am going to break down the product into two steps. So I am going to combine what I just did, cleaving that ester bond. Water is going to break my ester bond, and it is going to form a carboxylic acid and an alcohol. But since I have a base, something like sodium hydroxide, something like potassium hydroxide, my product, my carboxylic acid, is not going to stay there. It's going to react with the base and give me a salt and water. So the neutralization that we saw earlier will follow. But I'll do it in 2 steps. If you are asked this in a test, you don't need to do the 2 steps. I'm just doing the 2 steps so you can follow what's happening. Okay, so base hydrolysis. I'm going to have the exact same thing under basic conditions. So I am going to add something like sodium hydroxide in there. Okay, so now I'm going to have CH3, C double bond O, and I think I'll do it in 2 colors just because this is a little bit more intricate. O, CH3, so this is the alcohol part of my ester. And I'm going to add water to it. But on the arrow, what you're going to really see is water and sodium hydroxide. Okay, so it's hydrolysis under basic conditions. But I'm going to do the water part first and then take the sodium hydroxide on a second step. Okay, so when I put my hydrolysis, I'm going to repeat the 2 substances that I have here. I'm going to go back to my carboxylic acid and my alcohol, correct? So I am going to go back, and my CH3, C double bond O, is going to grab this water at a yellow part, and OH, and then this H went in there, right? And I'm going to do that in white so we follow it. So I'm going to have this guy. That's what we just had. That's acid hydrolysis. But then I said, oops, this is not my final product because I have a base in the same container that I have an acid. So this is a base and this is an acid. What do acids and base do? They neutralize. So I'm really taking step 1, the HOH, and step 2, the sodium hydroxide. Now I'm going to say, oh, I had sodium hydroxide. So the sodium hydroxide is going to neutralize my acid. And my H of my carboxylic acid and my OH of my sodium hydroxide will form water. So I get salt and water. So this is the real product. The real product is going to be CH3, C double bond O, single bond O minus, that's a double bond, and what? And an Na. Plus water. So my 2 products of basis hydrolysis is my alcohol and my salt. Salt and alcohol. Yes, and water. You can write plus water. Or minus water here. Okay, so basis hydrolysis does not give carboxylic acid and alcohol. It gives salt and alcohol. Because your base is going to react with your carboxylic acid and will neutralize it. This reaction right here, basic hydrolysis, is also called saponification. And let me tell you what that means. Saponification. Saponification from the old times, from Latin, the term facere means to make, and sapo means soap. So your great-great-grandparents, great-great-great-grandparents, they probably didn't have a Publix or a Winn-Dixie to go to buy soap. They had to make their own soaps. And this is what they did. They would take an ester from lard. Lard is an ester. And the only difference is that you have your ester group, and this is your ester group right here. But instead of having one carbon, when you have lard, you're going to have many, 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 many more carbons. So you're going to have, I'm going to repeat this, but instead of having one carbon, I'm going to have many, many more. Okay, so I'm going to have a squiggly line, and every squiggly line, we remember it means a carbon. So it's a CH2, and 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 I don't have room, so I'm going to stop there. And that last one is a CH3. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Really, you have 14, 18 carbons when you have lard. You have a long chain carboxylic acid, but it's an ester. That's all it is. And they would take it with lye. Lye is a very strong base. And they would mix the lard with the lye, and what they get is this same thing, but instead of having only one carbon, we're going to have all the 18 carbons over there. So I'm going to rewrite this and make my ester turn into a salt that's so much bigger. So it's going to be a CH2, 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 again and again and again. And as many CH2s as I had, I'm going to have in here. And again, these are long term. The last one is a CH3. And that's what they called a soap. And I got to tell you a story, because this is pretty close to home. It hits home when I tell this lesson. When I was in high school, I really honestly didn't know whether to study chemistry or what. I would take a course in psychology, and I wanted to be a psychologist. And I would take a course in art, and I wanted to be an artist. And I would take chemistry, and I wanted to be a chemist. And I wanted to be an engineer, and I just wanted to be everything. So I said, like, okay. I narrowed it down eventually to engineering or chemistry. And then I talked to this guy, and he said, you really don't know whether you want to be a chemist or an engineering? Answer this question for me. What's more interesting to you? To learn how to make soap, or to understand why do soaps clean? And I go like, okay, I had to think about this one, hard and strong, because this is going to decide a big chunk of my life. Once I learn how to make soap, that's going to be boring if I just keep doing the same thing again and again and again. Maybe I can make it more cost efficient or in better, more efficient ways, but to me it was why do soaps clean was much more interesting than how to make soap. So let me go ahead and tell you why do soaps clean once you have the structure of a soap in front of you. When you have a soap, you have this structure. A soap is a salt. That's all it is. It's going to have a positive and a minus. Okay, so at the beginning of the lecture I put the plus and minus in there. That's an ionic end. That's ionic. And the ionic is very polar, so it's going to be loving water. It's hydrophilic. It's soluble in water. Okay, so if you're going to wash your hands and they're oily, or if you're going to wash a pair of jeans and they're dirty and oily, the oil and the water do not mix. But in here you have a molecule that has an ionic head. This is a head that's ionic. And then it has a tail. CH2, 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 repeating 18, 20 times. And that's very nonpolar. The nonpolar section is going to love your dirt, your oil. The oil doesn't dissolve in water, but the oil is going to be bound to your nonpolar tail, and that oil is going to go down the drain because the head is attached to the tail, and the head is hydrophilic. So hydrophilic means water loving, and hydrophobic means you hate water. A soap has dual polarity. So it's a pretty spectacular molecule that has both a polar head and a non-polar tail. And in our next module, our esters will grow. We will form this type of molecules. So all we're going to do is change Instead of having one CH3 here, we're going to have many CH2, CH2, CH2s, and make it lard, a fat. And that's how your great-great-great-grandparents made soap. Okay, any questions in there? No questions in there? Not yet? Let it sink in. Do you want to go back and ask me questions on 9 or 10 alcohols or carbohydrates or anything like that? We leave it here for this one, but I do need to know. Yeah, you have a question in 9?
It was about, I think, 11, but I can ask you after class.
No. This is after class. We have time. We have the auditorium for another 15 minutes.
Okay.
And you have a test coming up, so
Okay.
I'll stop the recording.